Yeah, so my name is Mohamed Salani. So many thanks to the organizers for the opportunity to be here. And many thanks to Frédéric Barbaresco. I have known through LinkedIn, and I met him virtually. And through him, I discovered the Souriau group Thermodynamics. For some of you, I left the academia some 25 years ago. That's why you see Landesbank Baden-Württemberg. But I'm doing research again privately, so not for the bank, more or less for myself. And I was a little bit, I Googled if there's any link to Souriau, and I found that one of my professors during my diplôme d'études approfondies in Dijon was Moshe Flato. And Moshe Flato was a student of Andrei Lechnorowitz, who was also the professor of Jean-Marie Souriau. And I think that themselves, they know each other at one point of time. So it's like back to the roots for me, and I'm so happy to be here. So as I said, yeah, I'm more or less now for the last 1 year or 1.5 years working on this subject. So please be. Yeah, I'm not mastering everything like you, so for sure I will need your help if something is not as it is. So what I did here is, you know, as a mathematician, if you want to understand things, the best thing is to try to have an objective, and after speaking with Frédéric, I tried to understand the Lie group thermodynamics through trying to apply the whole tools in the polysymplectic framework. And as you know, polysymplectic geometry is a vast and a very large area, and it has been let's say a part of it has been introduced by Christian Günther, and who tries to apply it in the field of fields theory, and then it has been developed by Maruro and others, and Frédéric was the first one who has tried to apply it in the field of Lie group thermodynamics of Jean-Marie Souriau. Then with François Gay-Balmas, they have tried also to apply it in a very general framework. So what I did is the following. This paper was like an entry point for myself, just to try to understand. Oui, pardon. So, as I said, this paper was like an entry point for myself, just to understand the tools and to see what we can do about the coadjoint orbits in the polysymplectic model. And if you are interested to know where we are standing at the moment about the polysymplectic and the cosymplectic area, there are 2 papers that have been published in the last months. So I added the bibliography of them. So if you are interested, then you can see there what is the state of the art of this theory at the moment. So the best thing is to begin with is to have the definition, or how we can define the polysymplectic manifolds. So in the most, let's say, basic definition is to see it like a collection of k closed two forms which are closed, and the intersection of their kernel is reduced to the to zero, or to yeah. And then, as we have seen before, we have all this machinery with a Lie group and the Lie group action, and which is also defined in a standard way, because you will define your action in such a way that for every component of your two form, you will have that the phi star indexed by G of every omega J will be itself omega J. Then after, we can define, as before, the momentum map for every polysymplectic action. So it's the same definition, no, only here we have to define it component-wise. So I think we can skip it because it is the same definition as before. We can define also the adjoint action and the coadjoint action, and also component-wise. And here we define also, just be careful. The coadjoint action will be defined as the composition between the element of the dual and adjoint applied on the inverse of the element of T. Okay. And in the same way, we will define also the equivariant moment map and also the polysymplectic cocycles. So let me skip that also. And as before, we have to define also the polysymplectic cocycles. And I think that you are now more or less used to the same ideas, and we can also go a little bit ahead of that, because that are the same ideas, only defined component-wise. So what is interesting in the Jean-Marie Souriau model, so now we will have that the element of the Lie algebra will be this generalization of the inverse temperature, and we will have this pairing between the elements of our algebra and dual. I will speak about that in my second talk, because I will have a second talk where we will speak more about this the model in a more, let's say, explicit way. Here I will try more to speak about the structure of the coadjoint orbits in the polysymplectic model. But we have to notice that in this model we need some conditions. For example, that we have to take omega as the largest open where these both integrals are defined, because we need to define the Gibbs densities, and they are not defined on the whole algebra. That's why we need that, and we will assume that omega is not empty. So how is Souriau Lie group thermodynamics defined, or how is this model is defined? I mean, if you are coming to this to the GI's meeting, for sure you have been seeing these equalities and formulas many times. But I mean, it's part of it, and I will have to define it again. So we have the position function, which is defined as the integral of the exponential of the pairing between the momentum map and the geometric temperature. Then we can define the Gibbs probability densities associated to each beta in our omega. Then we have the phi of beta, which is the log of minus psi of beta. One other interesting quantity is the heat, which will be very interesting in the second talk. And it is the derivative of the Mathieu potential. And what is very important also is we can see it as the expectation of our momentum map. And it is an element of the dual algebra. And don't forget that we are now in our polysymplectic framework. That is, it's not anymore in one-dimensional, let's say, dual algebra, but in our k-dimensional Lie algebra. And all this can will lead us to define our the entropy. And the entropy, as in the standard case, we can define it as the Lejeune transform of the Mathieu potential. And that is the good thing with this, with the Günther polysymplectic framework, because you can really go far away and transpose the whole machinery as in the standard case, and everything goes smoothly. After, you will get some problems because, you know, nothing, there is no free lunch, as we are saying in the bank. But okay, I mean, until now, everything is going smoothly. And then you can define also the entropy, but now in a geometry way, because as I said, you define the entropy using the Lejeune transform, but you can see it also as oh, pardon. Okay, yeah. You see it here as the Shannon, as the axiomatic definition, but here is it as a geometric definition of the entropy. Okay, so now we let me come to the first, let's say, result. But as I said at the beginning, all the results are known results. So these results have been done in this paper of Marrero. They have tried to generalize this reduction theorem, where which is known in the symplectic way, where you take symplectic manifold and you quotient with G, and you take the inverse of mu, and you quotient, then you can get the one form, and you see what I mean. So they use that to have also the same result there. So let us have, as I said at the beginning, G is a Lie group, and we have its Lie algebra, and you have this its dual. And we take now T1 and 2K as an element of our dual algebra, but now in the polysymplectic framework. Now we have that our key coadjoint orbit in the same manner is defined as the coadjoint of 2,1 at 2K. And as we know, we have seen that before, that now in this case, we have that our omega on the coadjoint orbit will be plus minus nu applied on the Lie bracket of xi and eta. And we have also now in the polysymplectic framework or context that the tangent space of our orbit will be also given by the infinitesimal generator of the coadjoint action. So that's still true. And now we will define the canonical projection going from our orbit in the polysymplectic model to the orbit for every tau. Okay, then we can see that when we will project our infinitesimal vector, we can project it in fact on every component or on every infinitesimal vector in u g. And now using these facts, we can see that the tangent space of the whole polysymplectic orbit is now a subset of the product of every tangent space of every orbit to 1 until 2K. And with this, we can see that the instantaneous vector of the whole on the polysymplectic dual algebra, you can it's equivalent, and the let's say and the vector composed by every instantaneous vector on every G star. And the theorem is the following, that if we take that the omega tau G is the symplectic structure of the coadjoint orbit on every orbit in the components of our vector tau G, then the family omega tau with upper script given by the projection of every omega tau is a K polysymplectic structure on the coadjoint orbit. Okay, and how we do that? As we said at the beginning, we need to have closed two forms, and we need to have that the intersection of the kernel is 0. And we'll write the definitions of the omega, and when we write that, as we said, normally that will be plus minus nu of G. Please. And we take now xi in the intersection, and this means that nu of G applied to this xi and eta must be equal to 0 for every eta, and this is equivalent that that its instantaneous vector has to be equal to 0. And then we use the identification, and this means that it has to be 0, and it is in the Kern. So that is more or less the proof. So yeah, and so this proof can be also generalized in the case of non-null cohomology. This means when we have cocycles, and here we have also the orbit, and the orbit we can write it now as the adjoint plus this theta, and theta is the one cocycles as we have seen before, and here we can use the same argument as before to get the same result. And this result has not been part of this article I used before. So it is, let's say, yeah, new result, just to see that normally you can use the same machinery to get also a generalization to the case where you don't have zero cohomology. One of the problems. How long do I have still?
Well, should, 2 minutes. Yeah, 2 minutes.
Okay.
Yes.
Yeah. So just to say 2 words about Poisson structures. In the polysymplectic case, you don't have a Poisson bracket, because it's not like in standard case, because you have problems with the Leibniz identity. So that's why you have to look for other ideas to define the polypoisson structure. What some Spanish guys have tried to define. What I did use to show also that that the coadjoint orbits have also such structure. Okay.
Thank you very much.
You're welcome.
Are there any questions or comments?
Thank you, Professor. Gaussian distribution is a typical model in the Souriau Lie group thermodynamics. Could you please give us a typical model in your setting, in K polysymplectic structures for such a model? Thank you.
I didn't get it. Could you repeat, please?
He would like to have a model for the specific model for polysymplectic structure system. Basically, you want an example.
Yes,
Yeah, an example.
So a concrete example.
Yeah, right. Something.
Yeah, to be honest,
there is not, you have, not for the Souriau model, but for the case in Euclidean space, you have the Gaussian, which is the density of maximum entropy, and you have the case, or you have the density of maximum higher order. So you add hyperparameter of Lagrange, and you have high order moments, and you can define like high order Gaussian density. So it has been done, but for Euclidean space, for Gaussian, not for the Souriau model. But I invite you to try to find the extension. So it exists, but for in Euclidean space, you can define maximum entropy of higher order. And it is when you have a rarefied gas, when you have a rarefied gas. The physical meaning is that you have few particles. So you have a Gibbs equilibrium, but as you have few particles, this Gibbs equilibrium has a variances. Okay? So it fluctuates, and so it's why you need higher order moments and higher order temperature to describe this fluctuation, because you have not enough particle to have a stable Gibbs equilibrium. It is a fluctuation of the Gibbs equilibrium.
Okay.
Thank you for your question. Are there any other questions? Okay, so here there is a question.
My name is Mama. Please, I speak in French.
Please.
Ok, je veux parler en français.
Oui, bien sûr.
Ok, merci beaucoup. Déjà, merci pour ce brillant exposé. Comme le professeur l'a dit, Coadjoint définit sur cette variété une nouvelle métrique en définissant un nouveau crochet, doit apparaître la notion de coséquence de Coadjoint. Donc, ce qui fait que j'ai une préoccupation à ce niveau. Parce que déjà, j'ai lancé un projet sur la thermodynamique, exactement un peu semblable à celui-ci. Mais j'ai cherché le lien entre ces notions et la notion de réseau de neurones sur le modèle de Souriau. Parce que déjà, j'ai lu quelques papiers où il construit les machines de Lénine en partant de la construction des paires de l'as. Et il parle de modèle de Souriau. Je veux exactement savoir quel est le lien entre les deux.
On peut en discuter peut-être après, hein, parce que maintenant, sinon ça va prendre beaucoup de temps.
Ok, merci beaucoup.